So my name is Sean Smith. I lead product management for GraalVM. And today, as I said, we're going to give a sort of a GraalVM in a nutshell, the core features and what it's all about in 30 minutes or less. All right, oops, my mistake. Let's keep going. So what is GraalVM? So GraalVM is known as a runtime, a high performance runtime. It makes applications run faster. It improves on efficiency, and you get those features in sort of three different ways. So the first one is as part of the Java runtime, the GraalVM JIT compiler provides speed up for Java applications and any of their JVM applications, and we'll talk about that in a moment in some detail. The second way you get take advantage of GraalVM is through ahead of time compilation. So in this case, we take Java applications and Kotlin and Clojure and whatnot, anything that's Java bytecode, and we can compile them ahead of time into native machine code applications for different platforms. And finally, and a topic I'm not going to focus on today, just because of the time limits, is the support for running non-JVM native languages on GraalVM. And that's another application of the GraalVM compiler technology to provide a way to just-in-time compile other languages like Ruby, Python, etc., down to machine code, just like the Java apps you would deploy. So this is really interesting for people who have the need to mix languages together. So perhaps some JavaScript libraries you want to use in Java, you can do that with GraalVM. But I'm not going to focus on that today. So I will start with the just-in-time compiler, which is really easy for people to try out because it's just Java. So what we're doing with the GraalVM distribution, and today you can download GraalVM Enterprise from oracle.com. You can download Oracle Java SE. Those two different downloads have different configurations by default. And the key thing is that when you're using GraalVM, you're on the same hotspot JVM, but you're using the GraalVM JIT compiler. So rather than C2, which is the default compiler using GraalVM. The difference is that C2 has been around for quite a while. It's actually an excellent compiler. Of course, Java has excellent performance out of the box. It's written in C++. The Graal compiler is actually written in Java, so it's a Java compiler for Java. And it's had about 10 years of R&D investment on advanced compiler optimizations. So it does a really excellent job of bringing additional compiler optimizations that the C2 compiler doesn't include. So what's it good for? Well, it's just Java, right? So it's a JDK. It runs your typical Java applications, Spark, WebLogic, Tomcat, etc. Basically anything that Java runs on the JVM with the GraalVM compiler. It really is just for the final stage of your application execution. When your Java code, your bytecodes are translated down to machine code, that's where the GraalVM compiler kicks in. But otherwise, the experience of using it is fairly transparent. So performance is one of the main reasons people would choose to use GraalVM. And this is the Renaissance benchmark. It's just been updated for the GraalVM Enterprise 20.3 release, which just came out at the end of last year. Against OpenJDK 11, this is supporting JDK 11. You'll see here that there's a fairly broad range of benchmarks in this suite. The goal of Renaissance is to try and find representative real-world workloads. So there's some Spark in here, there's some Scala workloads, there's a bunch of different things. You see here on the far right, the geo mean of all the benchmark results is about 1.5. So GraalVM is accelerating the performance of these benchmarks about 50%. Which is quite a significant improvement in performance overall. And you'll see in some cases it's better, in some cases it's not significantly better. And that's because the types of workloads may or may not be amenable to the optimizations that the Graal compiler has. So certain things are really optimizable, especially if it's newer Java, so new Java applications using streams and other abstractions, and Scala especially, which has very high level abstractions, are really easy for the Graal compiler to optimize because it has a lot more freedom to move behind the scenes. In plain old Java code, like simple like loops and classes and old Java 4, 5, 6, there's not a lot additional that the Graal compiler can bring to the table for those old workloads. We at Oracle have obviously interested in using it ourselves, so we've certified WebLogic on GraalVM Enterprise. And we see on our internal benchmarks the same kind of mix of results. In some cases, we see excellent performance. In some cases, not a significant improvement, but up to 25% faster on, for example, JDBC is quite a significant result. I have seen customers getting better than this overall on throughput in terms of their application performance. It's actually it's good to know, because even WebLogic itself is not, again, significantly new code. It's a lot of the code has been around for a while. So we do quite well on WebLogic. On Scala, as I mentioned, we do particularly well. So the standard Scala benchmark, we're up to almost 3 times faster than Open JDK 8 here in this case. So if you're a Scala user, you really do owe it to yourself to take a look at GraalVM, because you'll probably see some significant benefits. And the Scala community has embraced GraalVM quite a bit. This slide's a little bit of a different way of looking at some of the data, or a different run of the data from Renaissance. This is one benchmark from Renaissance. And we ran it with different amounts of RAM to see what the performance was like. And what's interesting about this is the memory consumption and throughput sort of comparison or correlation. So if you look at the 6 GB column, it says, okay, we ran this benchmark, the naive base benchmark, with 6 GB of RAM, and we see in the green the OpenJDK time to run. We see the GraalVM time to run in red. It's a bit lower, quite a bit lower, almost half of that. But then if you look over 10 gigabytes, if we gave your Java application or this benchmark 10 gigabytes, OpenJDK does improve. And if you give more RAM to your JDK, it will improve the performance. Hotspot will get better. But GraalVM improves significantly also, sorry. But what's key about this is, if you look at the 6 and 10, GraalVM still exceeds the performance of the OpenJDK given 10 gigabytes. So that's a significant reduction in memory consumption. If you're deploying workloads to the cloud and you're paying for virtual machines, or you're sharing virtual machines where you have a certain amount of RAM available you've paid for, then cutting your RAM by, in this case, 40% to achieve the same throughput is a significant savings, right? You can deploy many more workloads on the same infrastructure. Anyway, yeah, it's a huge difference in terms of the performance profile between GraalVM and OpenJDK here. At Oracle, we have been using GraalVM ourselves. So the Oracle Cloud Infrastructure, the cloud platform, which is all across the world now in multiple data centers, we have been moving workloads onto GraalVM. One of the first that I have here was the monitoring service, which does telemetry. And they're gathering data from all the other services monitoring their performance. And in this case, you can see that we saw an OCI, the monitoring service saw a 25% reduction in garbage collection and an overall 10% improvement in transaction throughput. And what's interesting about this is that the 25% reduction in garbage collection is because of the compiler optimizations. So GraalVM does an excellent job at avoiding unnecessary object allocation, which takes the load off of the garbage collector. So if GraalVM uses techniques, let's say we have partial escape analysis, we will do some aggressive inlining across multiple methods, and we will detect whether an object has a lifespan that exceeds the scope of our optimization. In other words, most compilers and C2 can do some escape analysis. If you create an object in one method and it gets basically unused after that method, it can be allocated on the heap. GraalVM does a better job looking across multiple method invocations, a series or a chain, to see whether an object, what its life cycle looks like, and again, avoid allocation on the heap. So these kinds of things are significant when it comes to the overall performance. So by reducing the garbage we're producing, which reduces the garbage collector's time, or the time the CPU is spent on garbage collection, that CPU gets reallocated to your application. So even though you think of compiler optimizations as improving the code execution, making it faster, sometimes it's about actually avoiding generating garbage. That actually has an equivalent or a significant impact on the overall performance too. One well-known user of GraalVM is Twitter. Twitter's on our customer advisory board, and they have been seeing, using the Graal compiler, significant improvements in their throughput and significant cost savings. When you're Twitter and you're running at cloud scale with, as you can imagine, thousands of servers, savings of upwards of 12%, even 10%. If you can lose 10% of your servers and still support your customers, you're saving a lot of money. And so I like to tell people, if you've seen Twitter today, if you've read a tweet or sent a tweet, you use GraalVM because that's where that code is running over in Twitter. Okay, so that's the just-in-time compiler overview. Really, it's simply grab GraalVM, set your Java home, and go. You can try it out. It's very straightforward. Now I'm going to talk about the ahead-of-time compilation feature, which is a little bit more leading edge, I would say. So with the GraalVM ahead-of-time compilation feature, it's called Native Image. We can take your classes, jars, and other bytecode artifacts and basically compile them ahead of time into native machine executables. And we do that fairly straightforward way, and I'll explain it. But what's really great about these executables is they have a fairly small footprint on disk, so they're very easy to ship around if you want to distribute them. That also means it makes for smaller container images if you're putting them in containers, which is also advantageous. They start up really fast and they use less memory, and I'll sort of point out how that works. So the process is fairly simple. We have our native image utility, which really is a front end to a process that involves taking your code, loading them into the hotspot virtual machine, and then we do some reachability analysis. We take your main of your application and we trace through to find all the code that you need. And we compile it ahead of time rather than waiting for you to run the code yourself at runtime. We at that build time, we will compile the code and basically export it into an executable in the right format for Mac, Windows, or Linux. There's obviously different output per platform. What's really interesting about this approach is that we don't just compile all the code you need, that you've loaded up into the VM. Right, so if you load a jar in hotspot, you load a jar. In our case, we will walk through and only compile and add to your executable the classes, methods, and even the fields that you need. So if you have fields that are not referenced or methods aren't referenced or classes, whether it's in your application code, in some library that you've included, it's like if you use Maven and you add some Apache library to your POM, you pull in like dozens of others. You probably don't need most of it. We will get rid of all that stuff. And even the JDK classes, we only include the JDK classes that you absolutely require. So it means that these things are fairly small as a result, because you don't have everything you need. You don't have everything that's on your class path in that executable. So just in terms of the results of this compilation, you have to imagine that what we're talking about now is a machine code executable that's just, like any other application you may run, like a C or Go program. So you can see here on the left, this is a simple hello world. I've just run hello world because I want to sort of see the time it takes to boot up an application. In this case, you can see we're in the C Go range for performance. And kind of the message here is, if you're a Java developer and you're thinking of going to the cloud and you want to write microservices and you're thinking, oh, well, I guess it's time to learn Go. I need to really move on from Java. This is not the case, right? So you just need to take your Java application and basically compile ahead of time to get these kinds of performance results that you would like, and be competitive with the other technologies. The memory consumption is the same story. It's much lower memory consumption. The reason is fairly simple compared to a traditional JVM. That is that there is no JIT compiler. So that JIT compiler is gone. The code caches are gone. The profile caches that it would maintain are gone. Most of the classes that you would have normally loaded, as I said before, they're gone, so they're not loaded into memory. So we really do have very minimal footprint. You still have garbage collectors, and you still have garbage being created by your application, but the footprint is significantly lower than if you're running on the JVM. Now, to sort of give you a peek inside of these applications, what it looks like from the CPU and memory consumption when these things boot. We took this little hello world. It's like it's a little REST service, so it's a hello REST service. And we ran it on JIT mode on GraalVM, and we ran it as a ahead of time compiled executable. On the left, you see the just-in-time compiled version, and you see all that red is all CPU. So when you boot your application, there's a ton of CPU being consumed because the JVM is starting up. It is parsing the JDK class, JDK's class bytecodes, loading them into memory and making in-memory representations of those classes. It's doing the same for your classes. It's starting up the JIT compiler. It's creating these caches. It's starting background threads to do compilation. All kinds of things are going on. And then after you see here about 3.5 seconds of this app, in this case, excuse me, you see that it really settles down, right? So basically, all that init is happened, all that runtime init is over, and then you're just servicing the request. So every second, saying hello, hello, hello. So it does that, and you'll see the memory line here, the sort of green tealy line here. It goes up, and then it levels off at steady state at around 200 meg in this case. On the right-hand side, you see quite a different performance profile from the native executable. Because we don't really have to do any parsing of bytecodes, we don't load any bytecodes. There's no JIT compiler to initialize and run. There's not a lot less being loaded in memory because we've got rid of most of those classes. We have a very low memory consumption. You can see the line's very low, and the CPU is minimal. I mean, there's still an initial boot CPU hit because you start garbage collectors and so on up, other services that Java does require, but it's much, much less. And then you see along little ticks along the bottom of the line there, it's just those hits servicing those requests. So in general, it's a significant improvement in boot time and memory footprint, and CPU utilization is much better. So if you're a SpringBoot fan, this is a slide from Spring 1 recently. The team here, this is Sebastian Deleuze and Andy Clement on the right. They were talking about running the SpringBoot Pet Clinic application as a native executable. They're working on a project called Spring Native, and they are, I think they're on version 0.9, so they're almost ready to call it 1.0. But where they're at now, they ran Pet Clinic, and you see here the results of what they were able to achieve. The build time is quite low on the JDK. It's quite high on native executable, and this is where we'll talk about that in a moment. But look at the memory, right? You go from 417 megabytes of memory to about 100 meg. That's 75% reduction. The start time goes from 2.6 seconds down to 1558 milliseconds, right? 94% reduction in startup time, which is insane. The build time is basically because we've moved all of that compilation to the build time, right? So we have to ahead of time do all that walking of the trees, doing all the calculations of what's in, what's out, and then the actual compilation itself. So significantly more. So really, if you were, and then JDK of course amortizes this cost when you're running your application, so you're paying later basically. And in native image you're paying up front. So I think that if people are working with these ahead of time compiled applications, I would be, as a developer working with the JDK on the JVM, I would be developing and testing using JUnit, my ID, etc., and then including the native image generation as part of my compile time, or my nightly builds or daily builds. So I wouldn't do it every second because the time it takes is a bit too long, but it offers significant value. And the goal of all this, of course, is really containerization, right? People are focusing on cloud and containers. This is perfect for containerized workloads, which is why you see broad support from the community. So Spring, as I mentioned, they're working with the Graal team. Micronaut has excellent support for GraalVM Native Image because Micronaut is also focused on build time analysis and doing things like dependency injection at build time rather than at runtime. So it's designed for easy compilation and quick start. Quarkus is doing similar things. Heldon, of course, and even embedded Tomcat has support. So you can take an embedded Tomcat web app, compile it to native executable, and deploy. So what's great about this technology is that as it moves along, the community has really embraced it, and they're helping drive this to forward. So just to give you an idea of comparing what does ahead of time compilation looks like compared to just-in-time compilation, because there is no perfect solution for all cases, right? So there's, if there were a silver bullet, we'd all use it, but there isn't a silver bullet. So really, all your choices on technology depend on what you're doing and what you need. So if you look at the red line here, this is the request per second of a little benchmark for a native executable. So you can see it's sort of fairly flat. It's very predictable. It starts up, and then once it's settled down, it's going to be really consistent. So it's very predictable performance. The key thing is that it starts really fast, right? We saw that before, that SpringBoot application, right? 158 milliseconds versus 2.6 seconds. If you need instant response, then native executables are excellent, right? They're perfect for that. The blue line here and then the green dotted line, the blue line is GraalVM JIT Compiler. The green is actually JDK 12 in this case. They have a curve where they start off a bit slower because on the JVM, if you load your bytecode first, it's interpreted, then hotspot detects hot code. It doesn't hit time, or it does machine machine code generation with just-in-time, and it gets faster, right? So your code gets faster until you hit sort of a steady state. Now, what we see is because the just-in-time compiler has the time to learn, right? It's not even just your code, but it's actually how your code is being used in a given context. The kind of data path, the data is driving your code down certain paths. It'll optimize those pathways, right? So you get excellent performance, peak performance. So if you're looking for peak performance for longer running applications, the JIT compiler cannot be beat, right? So running on the JVM is ideal. If you're running small applications that need to start fast, like command line utilities or containerized workloads where container boot time is important to you, then ahead of time compilation starts to make sense. So, but there is no perfect answer. One thing we have going for us with GraalVM Enterprise Native Image is profile guided optimizations, however. So we're able to improve that red line, move that red line up by running the application and gathering some metrics and then recompiling the app, much like you would do for a C program. So profile guided optimization is improving the performance, and we expect to see better improvements in the future. Okay, so those are the key pillars of GraalVM, the key features that it offers. So our tagline is faster, smarter, leaner. So we're focused on accelerating Java applications, Java, Scala, Clojure, Kotlin, whatever runs, whatever compiles to bytecodes, it will benefit from GraalVM's JIT compiler. And we've also got this focus on fast execution of ahead of time compiled applications. The start basically feels instantaneously. And this is all done through about 10 years, like I say, about a decade of research at Oracle Labs into compiler optimization. So we have a whole team who are focused on, their whole career has been focused on compiler optimization technologies. And they've expressed that into, find really interesting ways to apply that. JIT compiler improvements, ahead of time compilation, and even support for compiling languages that are not native to the JVM onto the JVM. And as a nice result of all this optimization is also leanness, right? So we're using a lot less memory typically for the same application, less CPU, less memory, less garbage being produced. It's all just part of the package with GraalVM. So one really big piece of news that came out just a couple of weeks ago now at this point is that Oracle GraalVM Enterprise is included with the Oracle Java SE subscription. So if you've got an Oracle Java SE subscription, then you can download and use GraalVM at no additional cost. Really, there's no reason why not to give it a try and see whether you get the performance benefits you're looking for. Downloading GraalVM is just a matter of going to oracle.com. You can download it. Change your Java home and give it a shot. It's pretty straightforward, pretty low risk and low effort to see whether you see an improvement in the performance of your application. So if you'd like to learn more, again, go to oracle.com/GraalVM. You can find more details, documentation, download links, more webinars like this one. And we're also on Twitter at GraalVM. And do feel free to reach out to us. We'd love to hear from you. And with that, I'll say thanks, and we'll move on to the Q&A.